Good morning, I'm Manuel Zarzo, and today we're going to start with the Unit 5, which is Inference. This is a great unit that contains different videos, and in this video, Distributions in Sampling, I will start with the basic concepts. Well, okay, as I was saying, Inference contains in total Unit 5, 6, 7, and 8. So in this 5 unit, I will talk about distributions in sampling. Then in the Unit 6, we'll talk about inference in one normal population and also comparison of two normal populations. Next, in Unit 7, we will explain analysis of variance, which is called ANOVA. And finally, in the last unit, it will be about linear regression. Good. So about distributions in sampling. I'm going to start with some definitions that are the same about concepts that are basic in statistics that we explained in the beginning of the first unit of statistics. Population. The population is the set of objects or individuals that we are interested in obtaining information or obtaining some conclusions. Usually, we don't have the data corresponding to all individuals. Okay, this is quite often. For example, if we are in an industrial process that we are manufacturing a product or a piece, so all pieces or all products that are manufactured would be the population. Usually the population is quite large, so that we don't have the information about all the individuals. So what we do is to take a sample from the population. So the definition is that a sample is a subset formed by part of the objects of one population. For example, it could be that we take a set of 10 elements from this process. So sampling is the process of taking a sample, okay? And then by studying the sample, we're going to make some kind of study, some kind of statistical reasoning that is called inference in order to take conclusions about the total population. So the purpose of sampling is to obtain reliable conclusions about the population at the minimum cost based on the analysis of the sample. Okay, and then what is inference? Well, statistical inference is this process of reasoning to obtain conclusions about the population based on the analysis of samples that we take. These conclusions are with a known margin of error. Obviously, so we study the sample. For example, if the average in the sample is 10, we will say that in the population, the average is 10 plus minus some kind of margin of error. Good. Well, the golden rule of sampling is the following. The sample must be representative of the total population. And the only way to guarantee is this representativity is random sampling. Okay, this is an example. Imagine that we have a pie like this, a pie comprised of different kind of layers, which is quite often the case. So this is a good sample. This sample is representative of the total population of the total pie. Okay, the sample in this case is representative. But this is a very bad sampling. We have a population comprised by different layers. If we take a sample like this, okay, this obviously is a very bad sampling. Good. Okay, this seems quite obvious, but actually it's more real than what it seems. Because in the population, in real populations, sometimes the individuals are structured like in different layers. What does it mean? For example, one layer can be according to sex, according to age, place of living, okay, or levels of studies or income or whatever, okay? So people, when we want to get information about people, so people are structured in different layers. So sampling like this would be a very bad sampling, and then we have to keep in mind like this. So in the sample, the proportions more or less have to be maintained like those in the total population. Good. So characteristics of sampling. Okay. An adequate sampling size is important according to the size of the population. Obviously, if the population is very big, we need a sample size more or less quite big also. For example, if we want to study the intention of voting in all Spain, it's not enough to take just a sample of 100 people. Probably we will need some thousands of people. also according to the variability of the evaluated characteristic. If we want to get information about something, some characteristics that is that varies a lot, okay, so we will need a more large sample. If we want to measure or to get information about a characteristic which is more or less quite stable or not, that does not vary too much, so the sample size can be smaller. And also according to the maximum error allowed in the estimation. For example, if we want to guess the intention of voting in a general election, and then we want that information very precise, obviously we will have to ask a lot of people if we just want some kind of approximate estimation. So obviously the sample size is not so much. Well, random. The sampling has to be at random. It means that any unit of the population must have the same probability to be chosen as part of the sample. Okay, and for example, and this is a good case. This is the lottery. Probably you have seen this picture a lot of times. So inside we put a lot of small balls. So this sphere just goes round, and then some balls are extracted. So this is the most typical example of the case that all the units of, or all the individuals of the population have exactly the same probability to be chosen. But in a real context, this situation is not so theoretical or so ideal, and then it could be not so easy to take a random sample. But how to take a sample at random? For example, imagine that we want to select 100 people to be representative of all Spaniards, of all people living in Spain. Well, we can take different approaches. For example, we can say, let's generate a software or a program that generates at random telephone numbers. So we just call the people, and then once we have gathered a group of 100 people, that could be a possibility. So we have a group of 100 people that have been chosen at random. Yes, obviously, this is a random selection. But is that a good sample, a good way to take a sample? Well, another possibility is to study the structure of the population and try to maintain the same structure in the sample. For example, if I know that 50% of people living in Spain are men and 50% are women, so this is a good idea to try to keep the same proportion in our sample. Or if we can get the information about the distribution of age in Spanish people, we can more or less try to keep the same structure also in my sample, or according to cultural level or city. For example, if we know that 10% of people living in Spain, they live in Madrid, more or less, we should have the same percentage in our sample. Okay, so taking a good sample of people when we have to conduct a survey in a large population of people is not so easy sometimes. So this is like the difference between random sampling, okay, like the case of the lottery, we have all individuals more or less being identical, and a stratified random sample, like the case of people that belongs to different social strata. By social strata means that we have people that are like structured according to age, sex, cultural level, and so on. Well, there's a part of statistics that deals with this, with how to take a good sample in complex populations. But in this subject, as it is more or less quite basic, we will just deal with the case of simple random sampling. Okay, so we will assume that all individuals are identical, and then just by random we take the sample. Well, so imagine that we want to study if the manufacturing process of a certain product works correctly. So we take at random 10 elements and then we measure the length. Okay, so imagine that the values that we have obtained experimentally are the following. So this is the case of a large population. Okay, all the products that can be produced in this industrial process. Then imagine that we have the length, which is the quality characteristic that we want to measure, that we want to control. So this length has an average that we call M, and a standard deviation in the population that we call sigma. Okay, then we take a sample of 10 elements, and then imagine that we take the average of these 10 values, and the average is 360.89, and then we calculate the standard deviation, and for these values this is 18.11. So based on this information, what can we say about the population? Well, so there are different questions that we will try to answer in the following videos. For example, when we say that the population mean of the piece's length is 150, okay, this could be like the nominal value. Okay, imagine that our process, in theory, should produce these items with a length of 350. We take a sample and the length is not exactly that, so we have a deviation. But obviously, we will never obtain a sample average exactly of 350. So is that difference enough to say that the population has changed this average? Something like that, okay. So, well, it depends on what extent the sample average differs from the population average, okay, as I was saying. Imagine that the population has an average of exactly 350. If I take a sample of 10 values and I compute the average, we will never obtain a value of exactly 350. We have some kind of deviation. Okay? This deviation will be small or large depending on different issues. So in this case, we should study if this deviation is too much or not too much. Another answer that we will try to deal with is the following. Can we consider that sigma is 15? In this case, it was not exactly 15, it was 18.11. But imagine that in our population, we suspect that theoretically it should be 15. So do you have enough evidence to say that the standard deviation has changed? Okay. So this is the distribution in sampling. This is like we need to deal to understand what is the pattern of the distribution of the sample average, the sample standard deviation when we take different samples. Good. So imagine that this is the population. So we have a characteristic that we measure, like in the example, it was the length. Okay. So we have all the individuals. So there is an unknown constant that we want to estimate. We don't know, for example, the average of the population, or we don't know the standard deviation or the population or whatever. Yeah? For example, imagine that X follows a Poisson distribution. Imagine that we count the number of mistakes or the number of errors or whatever. If this is a discrete variable that will follow a Poisson distribution, the Poisson has a parameter lambda. Okay, so the goal for this sampling would be to estimate lambda, or it could be an exponential distribution with a parameter alpha. So the goal of the sampling would be to estimate alpha, or it could be a normal distribution with two parameters, the average and the standard deviation. And for example, we might be interested in estimating the average of the population. Okay, so we take a first sampling. SRS means simple random sampling, as I have explained in the previous slides. So we take a first sample, we can take a second sample, and so on, a lot of samples. Okay, so this is the population of all possible samples of size n that we can take from the population. And then from every sample, okay, I can apply a mathematical function. So with the values that I have measured from the individuals taking the sample, I can apply a mathematical function, okay, and based on that function, I will estimate the parameter. Okay, the parameter can be lambda in the Poisson, can be alpha in the exponential, or can be the average in the normal. Okay, so from every sample, I will get a parameter. And then this is the population of all possible values of this parameter. Okay, one from every sample. And then we call estimator. Estimator that we will represent like this. So the parameter with an asterisk like this is a mathematical function of the values that I have taken from the sample. Okay, this is important that you understand what it means. In the next slide, probably it's better explained. Okay, so x1 from xn are the values that we have taken in the sample. So we will apply a mathematical function to estimate the real parameter. We don't know the real value of the parameter, so we have an estimation, and then this is why we call it with an asterisk. Okay. So the issue then is, what is the mathematical equation that we should be applied to this sample in order to get the best estimation of the population parameter? Well, this is the issue that I will explain in the next slides. Well, imagine then that we want to calculate the average population length of the pieces manufactured in a process. Then I take a sample of 4 items and we measure the length. So we have 4 values from every sample. What is the best estimator for the population mean? Okay, so we can think different possibilities. Okay, so we can estimate the population mean by summing them and dividing by 4, which is the sample average, or we can just take the minimum plus the maximum divided by 2. Okay, in this case we are just using 2 out of the 4 values that we have from the sample, or we can just compute the median, or we can just compute the geometric mean. This is the formula for the geometric mean. Or we can just compute the minimum. Okay. Well, one concept that we have in this unit is the concept of bias. This is an important concept in distributions in sampling. The bias, okay, is, this is the definition, is the expected value of the estimator minus the real value of the parameter. Okay. Well, what does it mean? So imagine that we apply this. Okay, so we have 4 values, and then we just compute the minimum. And imagine that we repeat this operation in one sample, in another sample, in different samples. So I think that it is quite clear that we have a deviation. So if we have 4 values and I just take the minimum, so on average I will have a deviation with respect to the real value that we have, that we want to estimate. That deviation is called the bias. Okay. Once again, if I compute the average, so the mathematical expectation of this minimum, okay, and then I compare with the real value of the parameter, I will have a deviation. These values will be not the same. That deviation again is the bias. So this would be a biased estimator. But actually, if the sample size increases, the deviation with respect to the real value of the parameter will increase. Okay, so one definition is that an estimator is called unbiased if the bias is 0. Okay, so if the average of the estimator is equal to the real value. Okay? I think that it makes sense. Unbiased means that the bias is 0. Well, but for the rest of these estimators, the bias is 0, so they are unbiased estimator. But then we need some kind of criterion to decide which one is the best. Okay, that is a tough question. Well, the median is also unbiased, but only if the distribution is normal. Well, the best is this one. The best is the one that is unbiased, consistent, and also of minimum variance. So it's not enough that the estimator has to be unbiased. There are other conditions. The condition of being consistent and of minimum variance, which I will explain in the next slides. Okay, good. So how to assess the goodness of one estimator? Well, if imagine that we have 2 estimators for one parameter, okay, like in the previous slide, we had like different examples. So imagine that we take 2 of them, 2 possible estimators. Okay. Well, imagine that I take a lot of samples, and this is the estimated value for that parameter. And then imagine that I take another estimator, but the distribution of the estimated values is like this. It has a lower variability. Okay, a lower variability. Okay, which one is better? Obviously, the second. Okay, the second, because on average I'm getting closer to the real value. Okay, So the best is the estimator unbiased, but also of minimum variance. So if I have a list of different possibilities, so the estimator of minimum variance will be the same, will be the best, sorry. And what is consistent? Consistent means that when the sample size tends to infinite, the variance of the estimator will have to tend to 0. Good. Then, based on these mathematical conditions, it can be demonstrated that the sample mean is the best estimator of the population mean. Also, this is what we have. Okay, so this symbol means estimated value. M is the real value of the average in the population. The estimated value of the population average is the sample average. Then, the sample variance is the best estimator of the population variance. So if we want to estimate the value of the variance in the population, the best estimator is the variance in the sample. And then finally, if I want to estimate the proportion in the sample, the best estimator is the proportion in the sample, which makes a lot of sense. And then here, I finished this video about distribution in sampling.